Okay, so this is just a little test run of our video recording system. Just trying to show you guys a little lesson on exploring linear systems. So first off, we need to talk about what is a linear system and what do we actually mean by that. So first off, if we just zoom right in here on this line here, a linear system is just a group of two or more linear equations. And so today, to explore them, all we're going to do is actually just graph out different linear lines. In other words, graph out different lines and see what happens and what different ways they could possibly intersect one another. So the first one we have is y equals x minus 1. So if we think about y equals x minus 1, that means it has a y-intercept at -1. So I can plot my first point right down about there. And then its slope value is 1, so that means every time we go up by 1, we go to the right by 1. So I can plot a point there, and there, and there, and so on. Maybe I'll just fix this one a little bit, make it a little neater. That's a little better. Once I've got at least 3 or 4 points, I can draw a nice straight line through them, make sure it extends in both directions. And that there is my y equals x minus 1. Okay, so that's my one line. The other one is negative 4x plus 1. So positive 1 is now my new starting point. So I put my point right here. And then I need to go down by 4 and over to the right by 1. So 1, 2, 3, 4, and 1. So right down about there, down 4 over 1, something right about there. Now that I have those 3 points, once again, I can just connect a line that goes through each of them. Let's try that again, make a nice straight line. And this would be y equals negative 4x plus 1. So those are our 2 lines that we've drawn. Now, the follow-up question is if these are 2 linear equations, that means that put together, we've got linear system right here. So what does it mean to solve a linear system? Well, it means that there's a point that's on both lines at the same time. So if we try and locate that, that would mean it's a point that actually intersects the 2 of them. So we can identify that point right about here. So there is a point right there where the 2 lines intersect. We call that its point of intersection, of course, but we also sometimes call it the solution, or a special x and y value that works for both equations at once. So from there, we can think about what sort of options or scenarios could we actually have? Well, one of the options is that we have 2 lines that don't intersect at all. So I have one line that looks something like that, and another line that looks something like that. So if we think really hard about what's going on here, what do these things have in common and what do they have different? So they are going up or rising or increasing at the same rate, so their slopes are actually the same. But if we look at where they're going to cross the y-axis, well, one of them doesn't quite cross it, but we can see that it's going to cross it much lower down, somewhere down around here somewhere. So they clearly have different y-intercepts, even though they have the same slope. So as it turns out, when they have the same slope but a different y-intercept, we see that there is no point of intersection. And I'm going to use the short form POI for that, no point of intersection. The fancy name for that is we say that it's inconsistent, but you don't need to know the fancy name. Just know that one of these scenarios occurs when the slopes are the same, but the y-intercepts are different. There is actually no point of intersection between these 2. Another scenario might be the most straightforward and common type, where we have one line that goes maybe in this direction and another one that clearly does have a different slope. So let's say there's one that has a very different slope. Maybe it looks something like that. Well, if those two lines do have different slopes, then necessarily, no matter what, we know they will have a single point of intersection, which we can find right there. So if we analyze this just like we did previously, we say that the slopes are different. And in this case, we can also see that their y-intercepts are different as well. But even if actually their y-intercepts were the same, it wouldn't matter. As long as there were two different slopes, it's going to produce one point of intersection. And that's the key that we can focus in up top. There is one point of intersection. The last case is kind of a weird one, but it is important to talk about, because what about if we had a line, let's say I draw one just like this, make it a little bit straighter, something like that. And then what about if there was a different line, but it actually overlapped it completely? So maybe it's an equation that looks different at first, but as I start to plot out the points, maybe I realize that it actually runs completely along, right along, parallel to and overlapping this line. So in this case, I know it's a bit hard for me to demonstrate here, but I'm actually showing you two lines that are completely overlapping one another. And it's a strange situation that brings that about. The only way that could possibly happen is if both the slopes were the same and the y-intercepts were the same. In other words, you're dealing with two of the exact same line, even if their equations started off looking a bit different to start with. So what does this option really mean? Well, if they completely overlap one another, we say that there are infinite points of intersection. So infinite POIs. Write that a little neater. So those are the three basic scenarios. If we have the same slope, but different y-intercepts, then they're never going to intersect ever. As long as they do have different slopes in some way, they're going to intersect at exactly one point. Then the weirdest and rarest situation is if they have the same slope and they also have the same y-intercept. And in that case, we're dealing with two of the same line overlapping one another. On the previous page, or on the next page, excuse me, we'll go through and just see how we can do this without always have to graphing these out. And then we'll go from there. So now at this point, we want to try and summarize all the things that we've just learned. So we, again, ended up with three basic scenarios. So if the slopes were different, well, as long as the slopes are different, then there was only one point of intersection, one POI. The next line says, if the slopes were the same, but the y-intercepts are different. Well, that was the case where we had two lines that never crossed. In that case, because they have the same slope, but they're not overlapping, there's no point of intersection. They never touch one another. The last one was the strange one where both the y-intercept and the slope were the same. Those two lines overlap, and we say that there are infinite points of intersection. So that's the only case when there could be more than one point of intersection in this case. They're allowed to be one, none, or an infinite number. You'll never have two or three or four on their own, something like that. Okay, so let's practice this then. And we can always check our results by using a graph if we need to, but we can make some predictions about what the graph should tell us just based on what we know about slope and y-intercept. So let's do a little bit of rearranging first of each of these equations to make sure that they're in what we call slope y-intercept form. So if I focus in on this first equation that you'd have in your note, I can take this negative 2x and move it to the other side and make it positive. I can take this positive 4 and move it to the other side and make it negative. It gives me a result that says y is equal to, now it's positive 2x, subtract 4. Well, If we want to break that down a little bit, that means our slope value is the 2, and the b value, or the y-intercept, is -4. That gives us a starting point when we go to graph this later. For the other one, we don't really need to do any rearranging, but we might as well state its slope and y-intercept while we're at it. So the slope for this one is, of course, -1/3. That's the number attached to the x. This b value is 3. So if we take a look at what we have here, if we make a comparison, we can clearly see that these are different. And I'll just use the short form DIFF for different. And while we're at it, we can also compare these y-intercepts and say they're different as well, but that really wasn't as important to us. It's really the most important thing that we need to note is that these two slope values are different from one another. And there was only one scenario that produced different slopes from one another. It meant we had two lines that weren't parallel to each other, and so they could only intersect at one point of intersection. So our prediction should be that these, when we graph them, will only intersect at exactly one point. I'll give you the chance to try graphing those out, verify that you can get a little bit of practice in graphing, and see that they only intersect at just one point. You can always check it based on the filled in version of the notes as well. Let's try and do a bit of rearranging and make a prediction for the second example too. Once again, we just want to identify slope and y-intercept. So here, the slope value is 1/2. The y-intercept is 2. For the other one, we're going to need to do a little bit of rearranging. So if I take my -x, move it to the other side, it'll become positive. I can take my -4, move it to the other side, it's going to become positive as well. Then I'll just need an extra step at the end. So 2y is equal to x plus 4, all positive on that side. And then I need to divide everything there by 2. Y is all by itself. And then remember, I used to have just a 1 in front of the x. When I divide that 1 by 2, I have a 1/2 in front of my x now. That's my new slope. And 4 divided by 2 doesn't have to be a fraction. I can just actually divide that out. It's equal to 2. So let's make a little comparison here. Well, what we're seeing in this new one is that this slope is 1/2. And we're also seeing, just right up beside, that the b value is 2. So we have clearly the same slope. Use a different color and say, well, we have clearly the same y-intercept. So in other words, even though what we started with clearly looked like two very different equations, which can happen, what we see is that really when these are graphed out, they will produce an identical line on a graph. That means they'll overlap one another, and it's that weird situation where we have infinite points of intersection. Every single point will intersect. So take some time, try graphing those out for yourself, and verify for yourself that you do get two of the exact same line. And this last example, again, the first one is already nicely set up for us, just to quickly identify that the slope from this one is -2. The y-intercept from this one is 4. We'll have to do a bit of rearranging over here. I'll first move my 6x to the other side and make it negative. I'll move my -9 to the other side and make it positive. 3y then is all by itself, and I get -6x plus 9. Then I have to divide all three pieces in this equation, everything on both sides, by 3. That helps me get y all by itself. -6 divided by 3 gives us a nice whole number, -2 times x. 9 over 3, or 9 divided by 3, is just 3, or +3. So step back for a second and see what we have. That's -2 is our slope, and our b value is +3. So here we have a case where we can see, hey, the slope is actually the same once again. So we might start to think, hey, maybe we'll actually have two of the same line that completely overlap one another. But if I just use a different color to look at y-intercepts, we see that y-intercepts do not match up. So we're dealing with that case where we have the same slope and different y-intercepts. So that's two lines that are going to point in the same direction, but because they're not overlapping each other and they're pointing in the same direction, they are never going to intersect. So we should predict, and you can verify this by graphing them out on your own, that there are no points of intersection, no POIs. So again, take some time to use the graph space beside or a separate piece of graph paper to try and graph these out and verify that you did get the same things that we predicted in each of these cases.